Every serious developer who has tried to put OpenClaw into a real production workflow has run into the same wall. The agent is brilliant when it works, and completely unpredictable when it doesn't. One run, it chains the tools in the right order. The next run, it halts mid-workflow, asking a clarifying question, burns 3 times the tokens, and produces a different output structure. For personal automation, that unpredictability is tolerable. For a corporate pipeline that processes customer data, initiates financial operations, or pushes commits to a production repository, it is a hard blocker. Lobster is the feature that removes that blocker entirely, and it does it by taking the LLM out of the driver's seat, on everything except the tasks it's actually good at. Lobster is OpenClaw's native workflow engine, released in February 2026. The core idea is deceptively simple. Instead of asking the LLM to orchestrate every step of a multi-step workflow at runtime, you define the pipeline as a typed data structure in advance, and the Lobster runtime executes it deterministically, step by step, JSON piped between steps, with approval gates halting execution before any side effect fires. The LLM still participates, but only within individual steps where reasoning is actually needed. The orchestration layer between steps is completely removed from the LLM's control. The result is a tool that behaves identically every time it runs, costs a fraction of the tokens of a free agent workflow, and produces an auditable execution log that a compliance team can actually sign off on. To understand why Lobster is architecturally significant, you need to understand the specific failure mode it was built to solve. In standard OpenClaw operation, when you give the agent a complex goal, say, triage your inbox, categorize all emails received in the last 24 hours, draft responses for the routine ones, and flag the critical ones to Telegram, the LLM has to orchestrate the entire sequence. It decides which tool to call first. It decides what arguments to pass. It reads the output of each tool call, reasons about what to do next, and issues the next tool call. This happens at every single step of the workflow. The problem is that this LLM as orchestrator model is expensive, slow, and fragile in 3 distinct ways. First, every interstep transition costs tokens. The LLM has to read the full output of the previous step, hold the entire workflow context in its context window, and reason about the next action, even when the next action is completely obvious from the workflow definition and requires 0 reasoning. Second, LLM orchestration is non-deterministic. The same prompt with the same input data can produce a different sequence of tool calls on different runs, different on different days, different if the underlying model version changes. Third, LLM timeout errors accumulate across long workflows. A 20-step pipeline where each step has a 2% chance of a timeout error has a 33% chance of failing somewhere before completion, which means a third of your automated workflows are dying mid-execution. Lobster addresses all 3 problems simultaneously by moving the orchestration logic out of the LLM entirely and into a typed runtime that executes a predefined pipeline graph. The core design pattern of Lobster is what the official documentation calls small CLI plus JSON pipes plus approvals. This is a deliberate and elegant architectural constraint. Here's how it works in practice. You build each step in your workflow as a small CLI command that speaks JSON. It takes JSON input on stdn, does one specific thing, and outputs JSON on set and out. That's it. One command, one responsibility, clean JSON interface. These commands can call any OpenClaw tool via openclaw.invoke, run any shell command, invoke any external API, or call LLM-Task for steps that genuinely need LLM reasoning. You then chain these commands into a Lobster pipeline definition, a structured file that specifies the sequence of steps, what JSON flows between them, and where approval gates should pause execution. The entire pipeline runs as a single Lobster tool call from OpenClaw's perspective. The agent issues one call. Lobster executes all the steps in sequence, and OpenClaw receives a single structured result envelope at the end. The output envelope is one of three statuses. OK when the pipeline completes successfully, needs_approval when execution has halted at an approval gate and a resume token is waiting, or cancelled when a gate was explicitly denied. The resume token is significant. It means a halted workflow can be continued at a later time without rerunning everything that already completed. You approve the pending side effect, pass the resume token back, and the pipeline picks up exactly is the feature that makes Lobster genuinely enterprise viable, and it is worth understanding in precise detail because the implementation is more sophisticated than it first appears. An approval gate is a step in the Lobster pipeline that is tagged as a side effect. The definition of a side effect in the Lobster context is any operation that has an observable consequence outside the pipeline's own execution environment. Sending an email, posting a GitHub comment, initiating a payment transaction, pushing a commit, sending a Telegram message, or modifying a database record. When Lobster reaches a step tagged as a side effect, it does not execute it. It serializes the pending operation, the exact command it was about to run, with the exact arguments it had computed, into a human-readable preview, and pauses execution. It returns a needs_approval envelope with a resume token to OpenClaw, and OpenClaw surfaces the preview to you through whatever interface you are using, WhatsApp, Telegram, the CLI. You see exactly what the pipeline wants to do. You either approve or deny. If you approve, you pass the resume token back, and the pipeline executes the side effect and continues. If you deny, the pipeline is cancelled and nothing fires. The power of this model is that it is not asking you to review the intent of the workflow you already defined that when you wrote the pipeline. It is asking you to review the specific output of the LLM reasoning steps that fed into this side effect. You see the exact email that is about to be sent, with the exact recipient, subject, and body that the LLM generated. You see the exact GitHub comment that is about to be posted. This is a fundamentally different review model from a chatbot asking, "Shall I send the email?" It is a production deployment previewing the exact change it is about to make and waiting for a binary confirm or deny. Beyond approval gates, Lobster builds enterprise safety requirements directly into the runtime, rather than relying on each individual workflow to implement them correctly. The official documentation describes this as safety policy baked in. Because every Lobster pipeline is a typed data structure, rather than dynamically generated code, every execution can be logged in full detail, diffed against previous executions of the same pipeline, and replayed for audit review. A compliance team can look at any pipeline execution and see exactly which steps ran, what JSON went into each step, what JSON came out, which approval gates fired, who approved them, and when. This is the audit trail that regulated industries need, and that free agent OpenClaw operation cannot provide. The Lobster runtime also enforces a set of safety constraints that apply globally across all pipelines without requiring per workflow configuration. Timeouts are enforced at the runtime level if any step exceeds its configured timeout milliseconds. The subprocess is killed, and the pipeline fails cleanly rather than hanging indefinitely. Output caps prevent any single step from producing an output that would overflow the context window of the subsequent LLM step. Sandbox checks verify that file system operations stay within the authorized workspace boundary. Allowlists restrict which external CLI commands and network destinations each pipeline is permitted to call. These are not features you configure per pipeline. They are constraints the Lobster runtime enforces across every pipeline that runs inside it. This means a new workflow author cannot accidentally write a pipeline that bypasses timeout enforcement, overflows the context, or calls an unauthorized external endpoint. The safety surface is controlled at the runtime layer, not the workflow layer. One of the most significant recent developments in the Lobster ecosystem came from a community contribution documented on dev.to this February. Lobster's original step model was, linear steps run sequentially, data flows forward, no native loop construct. For many workflows, linear execution is sufficient. But for workflows that require iterative refinement cycles, a code review loop that runs until either the reviewer approves or a maximum iteration count is reached. For example, linear execution hits a hard Sub-Lobsters, nesting a lobster pipeline as a step inside another lobster pipeline. You define the inner pipeline as a loop body, one iteration of the code review cycle, and the outer pipeline manages the loop counter and the termination condition. The outer pipeline calls the inner pipeline via OpenClaw.invoke, inspects the output, increments the counter, and decides whether to call the inner pipeline again or terminate. Because OpenClaw.invoke can call agent-send to message other OpenClaw agent instances, Sub-Lobsters also become the foundation for multi-agent coordination patterns, a parent pipeline orchestrating multiple child agents, each running their own sub-pipelines in parallel, with the parent collecting and merging their outputs. Lobster's pipeline definition format is powerful but text-based. You write .lobster files by hand or generate them programmatically. For non-technical operators who need to build and modify workflows without writing pipeline syntax, ClawFlows provides a visual interface. ClawFlows is a visual workflow builder that compiles to Lobster pipelines. You drag, connect, and configure steps in a visual graph editor, and ClawFlows generates the underlying .lobster pipeline file that Lobster executes. This means the same Lobster runtime that handles programmatically generated pipelines also handles visually composed pipelines. There is no separate execution engine for visual versus code-defined workflows. The composability extends to agent skills as well. Individual agent skills, code generation, data analysis, file manipulation, API interaction become building blocks in the ClawFlows editor. Skills that were built independently can be wired together without modification because every skill speaks the same JSON interface that Lobster's pipe model expects. The result is that a non-technical operator can compose a multi-step automation workflow from existing skills without writing a single line of code, and the resulting pipeline has the full determinism, auditability, and approval gate behavior of any handwritten Lobster pipeline. One of the most practically important integrations in the Lobster ecosystem is the LLM-Task tool, which is specifically designed to be called from within Lobster pipelines. The problem it solves is the following. A deterministic pipeline is only deterministic in its structure, not necessarily in its content. The structure, which steps run, in what order, what JSON flows between them, is fixed by the pipeline definition. But the content produced within individual steps that require language model reasoning is still non-deterministic in the traditional sense. LLM-Task addresses this by wrapping LLM calls in a structured output contract. You define a JSON schema for the expected output, and LLM-Task retries until the model produces output that validates against the schema or a retry limit is reached. This means you can embed LLM reasoning steps inside a Lobster pipeline with a guarantee that the output flowing into the next step will match the JSON schema that the next step expects. The pipeline structure is deterministic. The content produced within each LLM step is schema-validated. The combination gives you a workflow where both the execution flow and the data contracts between steps are formally specified and enforced. The community has been running Lobster on real workflows for several weeks now, and the benchmarks that are emerging from Reddit and dev.to threads are concrete. For scheduled automation tasks that were previously running as free agent workflows, the shift to Lobster pipelines is producing token cost reductions in the range of 60 to 80%. The mechanism is exactly what the architecture predicts, eliminating LLM reasoning overhead at every interstep transition, replacing it with direct JSON piping. A 15-step email triage workflow that previously required 15 separate LLM calls to orchestrate now requires one Lobster tool call containing approximately 3 to 4 LLM calls within specific steps where reasoning is actually needed. Task failure rates caused by LLM timeout errors have dropped to near zero on Lobster-managed workflows, compared to failure rates of 15 to 30% on equivalent free agent workflows, depending on workflow complexity and LLM response time variance. The resume token mechanism means that even when a timeout does occur within a Lobster step, the pipeline does not lose its prior execution state. It can be resumed from the point of failure rather than restarted from GitHub automation workflows specifically. Lobster's approval gate model has been particularly impactful. A workflow that monitors open pull requests, runs automated code analysis, and posts review comments can now route every proposed comment through an approval gate before posting, giving the developer a Telegram preview of each pending comment with a simple approve or deny interface. The alternative, letting the agent post comments autonomously and reviewing them after the fact, is the pattern that produces the kind of rogue agent behavior that security teams and corporate compliance teams find unacceptable. Pull all of this together and the strategic significance of Lobster becomes clear. Every enterprise objection to OpenClaw maps directly onto a Lobster capability. The unpredictability objection is answered by deterministic execution. The audit trail objection is answered by pipeline as data and execution logging. The safety objection is answered by approval gates and runtime enforced safety policies. The cost objection is answered by token reduction. The fragility objection is answered by resume tokens and schema-validated interstep contracts. OpenClaw without Lobster is a brilliant but dangerous power tool that most enterprises cannot touch. OpenClaw with Lobster is a structured, auditable, approval-gated automation platform that begins to look like something a compliance team can sign off on. That is not a marginal improvement, it is a category shift. Lobster is not a feature you use because it is interesting. It is a feature you use because it is the difference between a workflow that works reliably in production and one that surprises you at 3 a.m. Deterministic execution, JSON pipes, approval gates, resume tokens, schema-validated LLM steps, runtime enforced safety policies. Every piece of this architecture is solving a real problem that real developers hit when they try to run OpenClaw on real production workloads. If you are building anything serious with OpenClaw and you are not using Lobster yet, you are building on the wrong foundation. Subscribe for a full hands-on tutorial series covering Lobster pipeline construction, Sub-Lobster multi-agent patterns, and Clawflow's visual composition. Hit like if this breakdown gave you a clear picture of what Lobster actually is, and drop a comment telling me which workflow you are going to migrate to Lobster first.